Have you ever wondered why the universe is the way that it is? What if down was up and up was down? What if positive was negative? What if time flowed backwards? It might surprise you to know that even scientists ask these questions. Some of the greatest minds of physics have spent their lives trying to determine why the universe formed the way that it did. It may also surprise you to know that the Big Bang is still an incomplete story, and there is a significant portion of time in the early universe that is still unaccounted for. And believe it or not, the flow of time, the polarity of a battery, and even the direction of a one-way street could provide us with answers for why we are here in this moment asking these questions. It all starts in the early moments of the universe, when space was very dense and everything was extremely hot. In fact, it was so hot that all of the contents of the universe were effectively vaporized. The constituents of matter had not yet cooled to the point at which quarks could form protons or neutrons, or protons and neutrons could form the nuclei of atoms, which would form elements, which would form us. At this point, space was filled with massive amounts of high-energy radiation, as well as a few particles of matter and antimatter. These electrons and positrons were flying around at high speeds, unable to interact. However, once space began to cool, the matter and antimatter began to annihilate with each other, producing even more radiation. Yet somehow, despite there being theoretically equal amounts of matter and antimatter, we still ended up with enough matter left over to form the entire universe that we know, and almost no antimatter. So this leads to the obvious question: where did the matter come from? If we started with equal parts of matter and antimatter, why was there an asymmetry in the reactions between them that led to the universe we know today? Before we answer that question, let's first talk about the difference between matter and antimatter. In the tumultuous 20th century of physics, which saw many revolutions in the way we understood the universe, including the theories of general relativity and quantum mechanics, Paul Dirac made his contribution to quantum theory, which predicted the existence of particles with the same mass as normal particles, but opposite charges. These complementary particles were called antimatter. The most well-known antimatter particle is the positron, which has the same mass as the electron, but with a positive charge. Another consequence of this theory is that when matter and antimatter particles interact with one another, they annihilate, or turn into a large amount of radiation. This idea follows from the discovery of Einstein, E=mc², you may have heard of it, which means that energy and matter are but different manifestations of the same thing. Therefore, it is possible for reactions such as these, or other nuclear reactions, to convert matter into massive amounts of energy. Now, how do we know that there isn't any antimatter in the universe? What if there were a distant antimatter galaxy that we just hadn't found yet, where the people were anti-people who ate anti-food? Well, of course we haven't searched the entire universe to make sure there is no antimatter. But we know that if there were an antimatter galaxy, then at some point it would have come into contact with some matter. And if it did, we would be able to detect the massive radiation produced from this collision. Therefore, because we don't see any flashing signs of a matter-antimatter war in deep space, we think it is safe to say that the universe is almost completely made of matter. So once again, what is the matter? Why is there no antimatter? Well, the short answer is that we don't know. We have some ideas, and there is an open field of research dedicated to answering this question, but at this very moment, the question of why we are made of matter is unknown. What ideas do we have? That is where we return to why forward isn't backwards. In quantum mechanics, we know of three fundamental symmetries: parity, charge, and time reversal. Parity refers to spatial coordinates, or direction. If we flip the direction of everything, then physics should behave the same, right? Charge is, of course, the electrical charge of anything, such as particles. If we flip the charge of everything, then electricity should flow backwards through wires, but the devices should all still work, right? And finally, if we record everything that happens in the universe, then play that footage in reverse, everything should just be reversed, right? These symmetries are abbreviated as C, P, and T, and thankfully for our sanity, if you flip all of these at once, then CPT symmetry together is guaranteed to be conserved. Unfortunately, these symmetries are not held individually. In fact, in some particle interactions in the quantum realm, physics does not behave the same based on direction. Changing the charge of particles changes their behavior, and reversing time does not mean that everything happens exactly in reverse. I know this might seem mind-boggling, but this just goes to further show how the ideas of quantum mechanics do not meld with the classical ideas that we experience in everyday life. It is weird down there. Anyway, how does this help to explain why we are anti-people? Well, the only reason we can think of as to why the equal amounts of matter and antimatter might have had a little bit of matter left over is that somewhere, at some point, there was an asymmetry in the reactions large enough to mess things up. So, if we study asymmetries like C, P, or T asymmetries in nuclear reactions today, then we can think in reverse back to the Big Bang and try to account for all the asymmetries that must have occurred back then to create the universe. It's sort of like walking outside, seeing that the ground is wet, and assuming that it must have rained previously. We obviously can't go back to the Big Bang and do an experiment, but if we assume that the laws of physics haven't changed, then we can discover things today and use them to explain the past. Therefore, the search for fundamental asymmetries in the interactions of particles is a very high priority in the fields of nuclear and particle physics, astrophysics, and cosmology, and many types of creative experiments have been devised to find examples of particles breaking symmetries. The first symmetry violations, which violated parity, were found in particles that exhibit the weak force interaction. The weak force, which is one of the four fundamental forces of the universe, is a force that goes on within the nucleus and is responsible for spontaneous nuclear decay, such as that which occurs in uranium. By studying the decay of certain particles, scientists were able to find one which seemed to prefer a certain direction. The fact that this interaction has a handedness shows that not all interactions occur in exactly the same way if you flip the spatial coordinates, and therefore, parity symmetry is broken. Current efforts to discover new asymmetries vary in their approach. One method searches for the electric dipole moment of the neutron. The neutron is an electrically neutral particle that makes up the atoms of all the elements we know. Since it is electrically neutral, we wouldn't expect it to react to an external electric field. However, we see in our experiments that if exposed to an electric field and kicked, it will wobble very slightly. This wobbling represents what we call the electric dipole moment. The fact that this dipole moment exists is another example of symmetries being broken, but we still don't know quite how much this phenomenon breaks symmetry. So, we continue building more precise experiments to measure this wobbling in an effort to determine if this can account for the asymmetry in the Big Bang. In addition to the searches for the neutron electric dipole moment, there are also experiments which test the nuclei of a wide range of different elements to see how they react to having neutrons fired at them from a gun. When these nuclei get shot with neutrons, the neutrons stick to the nucleus of the atoms. For a very short time, this makes the nuclei bigger and heavier, which is quite uncomfortable for them, as the nuclei tend to be rather self-conscious. So, they decay very quickly, meaning that the weak force takes over and they emit radiation in the form of light, some more neutrons, and maybe some other particles. From this rapid shedding of weight, we can measure the light radiation, also known as gamma rays, and see in which direction they are produced. This technique is known as neutron spectroscopy, and it is also a valuable tool in other nuclear physics and materials science applications. Anyway, when we shoot the neutrons at the target, we can polarize them, which just means that we pass them through a magnetic field and make them all turn in the same direction. They then hit the target, produce radiation, and we measure the direction that the radiation comes out. Next, we flip the polarization, shoot them again, and measure the direction again. If we measure the radiation coming out differently in the other direction, then we know that there is some asymmetry in the nuclear reactions based on the polarization directions of the neutrons. Boom, more asymmetry. By testing all the nuclei we can think of for this asymmetry, we can narrow down which ones can help us explain what happened in the Big Bang. So, long story short, the next time you feel the weight of the unforgiving flow of time bearing down on your soul, take a second to remember the fact that it is because of that flow of time that you are a person eating people food and not an anti-person eating anti-people food. But then again, how do we know that we aren't actually anti-people and that our food isn't actually anti-people food? How do we know that up isn't actually down and that right isn't actually left? What if we don't all see the same colors? Anyway, don't forget to season your food with your heart and season your mind with science.